Friends, welcome to Memoneet. I am Satiswaru, teacher of Memoneet. I am here to start with a new lecture on electrostatics, that is on electric flux and conductors. Hope so you are completing the daily targets, attending quizzes and also completing the videos. Those who have not joined the Telegram channel till yet, please do join because all the facilities will get right from there. Okay, so let's start it. Flux, I just want to tell about the area vector of different shapes. Let's say we have a circular plate here. Okay, a circular plate, and in the circular plate, uh, the area vector will be in which side? Which will be in the perpendicular to the surface area. Okay, perpendicular to the surface area. So this will be the area vector. Okay, let's say we have square plate. This is the sphere plate and the area vector will be perpendicular to this. Okay, what do you mean by the area vector? The area vector tends to that the cross section area. Okay, so let's say we have this mobile here. Okay, what is the area vector of this mobile? This is the cross section area through which we can draw the area vector. That is, the area vector will be in this side. Okay, or we can take in this side. Okay, this is not the area. Okay, this is the surface area and we are talking about the area vector, the cross sectional area. So this will be the cross sectional area through which we can cut it. Okay, so now the electric flux. Okay, electric flux uh, through a surface inside and in an electric field represents the total number of electric lines of force crossing the surface. It is a property of electric field. Nothing but this is a energy. This is a type of energy, or we can say in the electric field. Let we have the electric field here. Okay, this is the electric field here, and the total number of lines of electric lines of force crossing through the cross sectional area. This is the cross sectional area, and this is one of the surface we have, and the electric lines of force is crossing this CSA. Okay, cross sectional area. So this property is called as electric flux. This is electric. This is nothing but an electric flux. Okay. Out it is giving out the number of lines of force, okay, crossing through an area. Okay, the electric flux, that is phi is the flux, phi is equals to electric field into area vector dot a vector. Okay, E vector dot A vector, or we can write for the small element d phi is equals to E vector dot ds vector integration for the closed surface, and it is only defined for the closed surface. So it is defined for the closed surface. Flux as Q enclosed upon epsilon naught. Okay. Electrostatics states that the electric field, it gives the relation between the electric field in an closed surface, in a closed surface and the charge enclosed within the Gaussian surface, within Gaussian Gaussian surface. Gaussian surface is an imaginary surface we have taken. Okay, so according to our convenience to find out the electric field. Okay, let's say we have phi here. Phi is equals to E dot A, or we can write that is Q enclosed upon epsilon. Okay, let's say we have a spherical cell here. Okay, and here a charge Q is present here. So electric lines of force will go like this. Okay, So it will generate an electric lines of force like this. So the phi or electric flux we can write, that is q upon epsilon naught. Okay, let's say we have a square, sorry, cube. Okay, this is the cube, and on the one side of the cube, sorry, on the center, let's say we have on the center of the cube we have charge q. Okay, so the phi will be, electric flux will be q upon epsilon naught. But if we will say that from the one of the surface of the cube, you have to find out the electric flux from one of the surface. So how many surface in the cube are present? We have, so from the six surfaces we have flux, that is q upon epsilon naught is there. Okay, for one surface, so six surface contains six surface will have q upon epsilon naught. So one surface, the associated flux will be q upon 6 epsilon naught. Okay, likewise we will find out the flux related to that figure or that surface. Okay, the flux through the Gaussian surface is independent of the shape. So Gaussian surface can be of any shape. It can be, say, like a cylinder, it can be like a sphere. Okay, then flux through the Gaussian surface depends only on the charge present inside the Gaussian surface. So I have written that is phi is equals to E dot A, which is equals to q upon epsilon naught. But here the flux is only depend upon the charge enclosed within that surface. Charge enclosed within that surface. We know that the electric field, okay, electric field, if we have, let's say, here one surface and here the charge. Okay, so the electric field will be there there for charge present inside or outside the Gaussian surface. Present inside or outside the Gaussian surface. Gaussian surface. Okay. But the flux only depends on the charge present inside the Gaussian surface. Present inside Gaussian surface. Okay. So let's take an example here. Here we have charge q and it will generate the electric field like this. Okay, let's say it will generate electric field like this. So phi will be what? Phi will be equals to the number of flux coming into the Gaussian surface and the number of flux emerging out of the Gaussian surface. Okay, this will be equal. That is phi, the phi enclosed, phi in is equals to phi out. Okay, so here phi in will be equals to the flux enclosed will be equals to flux emerging out the surface. Okay, so here the net flux associated for this surface is 0. Okay, but the electric field will not be 0 because electric field will depend on the charge whether it is present inside or outside the surface. Then the third one, the flux through the Gaussian surface is independent of the position of the charges inside the Gaussian surface. That I have explained now. Okay. Then electric field intensity at the Gaussian surface is due to all the charges present inside as well as outside the Gaussian surface. I have just explained now. Okay. In a closed surface, incoming flux is taken negative, while outgoing flux is taken positive because n cap is taken positive in outer direction. That I have just told now. That is, this is the incoming flux and this is the outgoing flux. Okay, this is the outgoing flux or outgoing flux. Okay, Likewise, we will calculate in the problems. In a Gaussian surface, phi is equals to 0 does not imply electric field is 0. Here, the phi is what? 0, but the electric field is not 0 at every point of the surface, but E is equals to 0 at E is equals to 0 at every point implies phi is equals to 0. Let's say we have a surface here, and we'll find the electric field. Let's say it is having the spherical cell, positive, 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 and we have to find the electric field here. Okay, at the point P, we'll find the electric field that will be 0, because in the electric field, if we calculate within this region, there will be no charge, so electric field will be 0. But the phi, what about the phi? The flux is also 0, because this, the enclosed charge is 0, and the flux is directly depends on the charge enclosed. Okay, charge enclosed. So phi is also 0. When E is equals to 0, phi is 0. But when E is not equals to 0, okay, phi whether can be 0, can be 0 or non-zero. Okay. If a point charge q is placed at the center of the cube, it is q, then find out the flux through any one surface of the cube. Let's say we have cube here, and in the center of the cube we have the charge, that is q, and we have to find out the flux through any one surface of the cube. So this this charge q will have the electric field lines of force like this. Okay, for the whole cube, we have, for whole cube we have flux, that is phi is equals to q upon epsilon naught. Okay, so you have six surface. So for six surface, we have, that is q upon q upon epsilon naught. For one surface, we have q upon 6 epsilon. So this is the answer. And then a point charge q, this is q, sorry, the point charge q is placed at the center curvature of a hemisphere. To find the flux through the hemispherical surface. So let's say we have a hemisphere here, and the charge is present at the central curvature. So we defined that flux is always present in the enclosed surface. This is not enclosed surface, so let's enclose it. First we have to enclose it. Let's say this will be the complete sphere. For the whole sphere, the flux will be q upon epsilon naught. For the whole sphere, what will be the flux? Q, sorry, for the sphere we have q upon epsilon naught. Phi is equals to q upon epsilon naught. So for the hemisphere, that is half of the sphere, we have q upon 2 epsilon naught. Okay, it will be divided by 2 because we are taking it half. So this will be the answer. Field due to the spherical cell, by applying the Gauss formula, what we have learned before, we will apply those. Okay, so electric field outside, let's say this is our sphere here, this is the sphere here. Okay, and the positive charge will reside sorry, this is the spherical cell. Okay, will reside at the surface of the sphere, surface. Okay, so the if we take any Gaussian surface outside the surface, let's say this is outside the surface of the sphere, and we have to find out the electric field at this position. So so the flux, we know that phi is equals to E dot A, and that is equals to q upon epsilon naught, charge enclosed upon epsilon naught. Let the charge enclosed is q. Okay, so electric field, we know that electric field into A, what is A? Area of the cell, that is pi 4 pi r square. Okay, let the radius of the cell is r. R square is equals to q enclosed upon epsilon naught. So electric field is equals to q upon 4 pi epsilon naught r square. So this is the electric field for the spherical cell. I have discussed it earlier also in the electric field section. So electric field inside the spherical cell. Let's say we have a spherical cell here and we have to find out the electric field inside the spherical cell. But the charge is always retaining or residing at the surface of the spherical cell. So there will be no charge inside the spherical cell. Let's say we are taking here the Gaussian surface, one of the Gaussian surface. So here we can write E dot A, E dot A is equals to Q upon epsilon naught. But here the charge enclosed is how much? Is 0. So the electric field will be 0. At the sphere, let's say we have sphere here and sphere will contain the electric field inside sorry, the charges inside the sphere. Okay, it will contain the charges inside. Okay, so we have to find out the electric field outside the sphere. Okay, this let's say we are finding the electric field here at point P. So it contains charge q. Okay, so we have the electric field into A, that is equals to uh, q upon epsilon naught. E is equals to q upon A epsilon naught, and the area will be q upon 4 pi r square. Area is the, let's say we have the radius r is r. Okay, so curved surface area of the sphere is 4 pi r square. So we have q upon 4 pi epsilon naught r square. So this is the electric field. Let's say inside the solid sphere. Let's say we have here the solid sphere and charge is enclosed here. Charge is distributed within the solid sphere. We are taking the electric field in this. At the point P, we have to find out the electric field, and this is the Gaussian surface I have drawn. Okay, Gaussian surface. It is an imaginary surface I have drawn. Okay. So for the whole, let's say it has the radius r. Okay, and we are finding the electric field at some distance small r from the center. So for the whole sphere, that is 4 by 3 pi r cube. Okay, for the whole volume of the sphere, we have charge q. For the radius r, we small r, we will have the charge that is q upon 4 by 3 pi capital R cube into 4 by 3 pi small r. Okay, so 4 by 3 pi cancelled out. So we have that is q r cube upon capital R. So this is the charge containing in within the Gaussian surface. So we can write E dot A, that is 4 pi r square, small r square, because we are finding the electric field at point P. So the radius will be taken up to this. Okay, so q, what is the charge here? Q r cube upon capital R cube into sorry, upon epsilon. So r square, here r cube is cancelled out, only one r is remaining. So we can write the electric field. Electric field is equals to q small r upon 4 pi epsilon naught capital R. So this is the electric field for the inside the solid sphere. Okay, to infinite line charge having uniformly distributed charge is charge of charge density. Okay, so let's say we have an infinite charge here. Okay, and we have the lambda, that is equals to q upon L as the linear charge density. Okay, so we can write that is lambda into L. Okay, so let's take an Gaussian surface. So how we will take the Gaussian surface here? We have to take a Gaussian surface like a cylinder. Okay, this is the Gaussian surface for this kind of set. Okay, this is the Gaussian surface. We are trying to find the electric field at here. Let's say this is the distance r. So we have electric field, that is E or E into the area. What is the area here? Area of the the Gaussian surface is 2 pi small r into L. Okay, 2 pi RL is equals to Q upon epsilon naught. Q is lambda into L upon epsilon naught. So we have electric field as lambda upon 2 pi epsilon naught R. Okay, here L to L cancel. So this is the value of electric field of infinite line charge. It is conductors. So what are conductors? Conductors are the material that conduct electricity, or it can conduct the current also. Okay. So basically I am talking that any material which can through which the electricity or the heat can flow. Okay. So conductors are material which contain large number of free electrons which can move freely inside the conductors. So because of their free electrons, they can conduct the electricity and they can also conduct the heat also. So the free electrons are there in the conductors and in the insulator. This is why the electricity can pass through the insulator. This is why we are using the rubber while doing any work through the electricity. Okay, so so that it can conduct the electricity. Okay, in electrostatics, conductors are always equipotential surface. Conductors are always equipotential surface. Equipotential surface I have already discussed about it. That is the surfaces which have equal potential all throughout. Okay, the charge always reside on outer surface of the conductor. Yes, charge will never reside on inside the surface of the conductor. It will always have the always reside on the outer surface of the conductor. If there is a cavity inside the conductor having no charge, then the charge will always reside on the outer surface of the conductor only. Okay. So electric field is always perpendicular to the conducting surface. This we have discussed also. What is the properties of the electric lines of force? Let's say we have uh, conductor here, and the electric field or electric lines of force will be it is a conductor. This will touch the conductor like this, always perpendicular to the conductor. Okay, this is how the electric lines of force will touch the conductor. Okay, then electric lines of force never enters into the conductor. We can, if we will say that here a conductor is present and the electric lines of force will be like this can't be possible because inside the conductor there will be no electric lines of force. Near the conducting surface is given by formula, that is E is equals to sigma upon epsilon naught n cap. N cap which represents the direction and it is given as E equals to sigma upon epsilon naught. Sigma is the surface charge density. Okay. When the conductor is grounded, its potential becomes zero. Yes, because we are taking the potential of earth as zero. Potential of earth, that is equals to 0. When it is grounded, the potential will become 0. Okay. So when an isolated conductor is grounded, then the charge becomes 0. Here we have isolated conductor here and we are earthing it. Okay, so in the earth the potential is 0, so this will make the conductor also the potential of the conductor to be 0 because they are connected, interconnected, so they will have the same voltage or same potential. So for that we have, let's say this conductor have charge q and it will have potential v is equals to kq upon r. So when it will be grounded, it will be equal to that of earth. Okay, so for that the potential to be 0, we have to move the charge into the earth. So all the charge will all the charge will flow to the earth. So so that the potential of this conductor will become 0. Okay, then when two conductors are connected, there will be charge flow till their potential become equal. Let's say we have one conductor here, another conductor here. Okay, and this is connected through the wire. Let's say this is r1. Okay, the radius is r1 and this radius is r2. and it has charge q1 and it has charge q2. So what will be the potential here? Here the when it is connected through the wire, the let's say q1 is greater than q2, okay, and r1 is less than r2, okay. So we can write v1 is equals to k q1 upon r1, and v2 is equals to k q2 upon r2. From the above I have given the conditions, so you can predict that the v1 is greater than v2, so the charge will flow from the higher potential to the lower potential. So we have q1 minus q, and here q2 plus q. So the net potential will be equal in both the side. So k q1 minus q upon r1, that will be equals to k q2 plus q upon r2. The charge will flow from up to which time? When both the conductors will have the same potential, and this will be the this will be the expression when the charge will be flowing, okay, at the surface of the conductor. So the electrostatic pressure is equals to electrostatic pressure, that will be equals to sigma square upon 2 epsilon, sigma square upon 2 epsilon, local charge surface electric field due to the conducting and non-conducting uniformly charged infinite sheet. Let's say we have here one conducting sheet here, okay. The charge will remain on the outer surface. So let's draw the Gaussian surface here, okay. So we have E dot A is equals to Q upon epsilon naught. The charge will be equals to, we know that the surface charge density is sigma is equals to Q upon A, and the charge will be equals to sigma into A. So we have EA is equals to sigma into A upon epsilon naught. So area to area cancelled out. So E is equals to sigma upon epsilon naught for the conducting sheet. For the non-conducting sheet, we have charge on the inside, okay. So we have to take two Gaussian surfaces. So for the one, we have E is equals to sigma, sorry, we have E into A, that is equals to sigma A into epsilon naught, okay. But here the area, we are taking how much area? We are taking two areas, so this will be 2A. So the electric field is equals to sigma upon 2 epsilon naught. This is for the non-conducting uniformly charged sheet. That two large parallel conducting sheets placed at finite distance are given charge q and 2q respectively. Find out the charges appearing on all the surface. हम एक सरफेस लेते हैं, ये वाला एक कंडक्टिंग प्लेट है और ये एक कंडक्टिंग शीट है, ओके. So this is q and this is 2q. So we take this point as p. So the electric field at P, electric field at P, it will be 0, because electric field inside the conductor will be 0. So what the charges present on the side on the surface of the conductor? Let's say this is x, this will be q minus x, okay, and this is let's say this will be 2q minus y, okay. So the electric field at point P will be 0. So the if we write the electric field expression, that is q upon 2a epsilon naught, okay. So for the point P, the charge present on the left side, that is x, only x, okay, not q. Let's say it is x. It is x upon 2a epsilon naught plus, sorry, it is all another charges will be present on the right side. So this will be minus of q minus x upon 2a epsilon naught plus y minus of 2 y upon 2a epsilon naught plus 2q minus y upon 2a epsilon. Okay, so this will be equals to 0 because inside the conductor we have electric field 0. So we can directly write x minus of q minus x plus y plus 2q minus y will be equals to 0. So this will be equals to plus x here, plus my it is minus of 3q. Okay, and y to y cancelled, that will be equals to 0. So x will be equals to 3q upon 2. Okay, x will be equals to 3q upon 2. Like that we can find the value of y also. So point q is also 0, so we can write q upon 2a epsilon naught plus q minus x upon 2a epsilon naught plus y upon 2a epsilon naught. This minus of 2q minus y upon 2a epsilon naught will be equals to 0. So we can write x plus q minus x plus y will be equals to 2q minus y. Okay, so here we have that is x to x cancelled out, and this is 2y will be equals to q, and y is equals to y will be equals to q upon 2 plus x will be equals to that is q minus 3q upon 2, that is minus of q by 2, and y is equals to q by 2. So 2q minus y, that will be equals to 2q minus q by 2 equals to 3q by 2. So observe one thing, we have 3q by 2 here. Okay, and we have also 3q by 2 on the outer side. Okay, 3q by 2. Okay, and this q minus x we have minus of q by 2, and here also q by 2. So what we have observed, so the charge which is present outside the conductor on the outer surface of the two conducting sheets will be the sum, the mean of the sum of the these two. Okay, let's say we have two charges, two conducting sheets here. Here it is q and 2q. Let the mean, find out the mean here, that is q plus 2q upon 2, and here the charge will present q plus 2q upon 2. Okay, and this will be equals to 3q by 2, and this will be also 3q by 2. So how we will find the charges at the inner side? Just subtract one of the charges, that is q minus of 3q upon 2, that is equals to minus of q by 2, that is will be equals to minus of q by 2. Why we are subtracting? Because the in one of the conductor, that is this seed, have the total charge q. So if here 3q by 2 is present, so how much charge will be present in the inner surface? That is minus of q by 2. So that whole sum will be q. And if this have minus q by 2, so this the inner surface on the another seed will have the same magnitude but in opposite in sign, that is of q by 2. Okay, let's take another example. Let's say this is one seed and this is another seed, and it has charge q and it has charge 3q. Okay, so what the charge present on the outer side, this will be mean of these two seeds, that is q plus 3q upon 2. Here is also q plus 3q upon 2, that is 4q upon 2, that is 2q equals to 2q, and this will be equals to 2q. Okay, so 2q charge present on the outer surface. So in the inner surface, that is q minus of 2q, that is equals to minus of q. What will be present here? here just opposite in sign, equal in magnitude, that is q. Okay, what will be the present in the outer side surface of the 3q 3q conductor, that is q. Okay, so this is how we are finding charges in different different sheets. Okay, the surface of the sheets. Okay, for conductor like this, and another this is the hollow conductor. Okay, let's say we have charge q here is present at the center. Okay, so this will what this is the conductor. Okay, so this will induce one minus q charge here, and then the charge on the outer side of the conductor will be plus of q. Okay, but when we have, let's say this is one conductor and another this is hollow. Okay, and we have charge q here, and the charge q is also present on the outer surface. Okay, so we this charge q, the small charge q which is present inside, will generate or induce minus q here in the surface of the inner surface, and this will also generate plus of q charge in the outer surface. But when we will talk that if the charge present here, okay, this will be zero, because in the conductor the charges doesn't reside inside in this region. Okay, in this part the charge will not reside. Every charge will travel either to the free space uh, or to the surface area. Okay, have some charcha on spheres. Okay, the first is we take as hollow spheres. Okay, then conducting conducting spheres, then have solid conducting sphere and hollow conducting sphere. Okay, and then solid non-conducting conducting sphere. Okay, so in this we can have, let's say we have hollow sphere. In the hollow sphere the charge will reside always at the surface. Okay, so if we take the Gaussian surface for these three, the charge will reside at the surface only, at the surface only. Okay, so if we talk about the electric field at outside the sphere, let's say it have charge q and radius is r, so electric field outside the sphere is kq upon r square. Okay, it is let's say we take it as small r for the distance outside the sphere, small r square. Okay, it is for r, sorry, it is for r greater than r, that is capital R, which is the radius of the sphere. And when small r is equals to capital R, we have E is equals to kq upon r square, that is capital R square, that is a radius of the sphere square. Okay, when E is less, sorry, r is less than, small r is less than capital R, we have the electric field present inside this hollow sphere or conducting sphere or solid sphere. This will not have any charges here. Okay, so the electric field will become zero. So let's now talk about the solid non-conducting sphere. In sphere we have the charges reside uh, inside the sphere. So the charge q for the 4 pi, for the whole volume of the sphere, we let's say this is the radius r. For the whole volume of the sphere, the charge it contains, that is 4 by 3 pi r cube, we have charge q. And for the let's say we take an sphere, a small sphere inside it, it is, let's say distance is r. So for the r radius of the sphere, we have charge, that is 4 by 3 pi r cube will be equals to q upon 4 by 3 pi capital R cube into 4 by 3 pi small r cube. Okay, so this will cut down. We have QRQ upon capital RQ. So this much of charge, this QRQ upon capital RQ, this much of charge is present in this small sphere. Okay. So now let's write the electric field at different position. So for the R greater than capital R, it means here, let's say our R is here. Okay. Sorry. But let's say the small r is here. Okay. R greater than capital R. So we have the electric field that is equals to KQ upon R square. For the R equals to capital R, we have E equals to KQ upon R square. Okay. For the R less than capital R, we have E equals to KQ. What will replace in place of Q? We have to KQRQ upon uh, capital R. Okay. This is the value of Q gone and in upon R square. So it is upon R square. So this will cut down. So we have KQR upon RQ. So this is the value of the electric field. So now let's look to the potential. Okay. Have potential V is equals to KQ upon smaller, and for these two we have potential is equals to KQ upon capital R, and this is equals to V will be equals to KQ upon capital R. Potential V is equals to KQ upon smaller, then this will be V is equals to KQ upon capital R. But here in this case, when the R is at the point where we have taken is less than the capital R, that is radius of the sphere, the potential will be equals to 3 upon 2 R cube 3 R square minus R square. This will be the potential, because here the self energy in fact is taken out, that is self energy for the conducting sphere is kq square upon 3 by 5 kq square upon R. Okay. Potential energy for the spherical cell, we have the the self energy will be kq square upon 2R. So this condition please remember it, because it will directly come in the exam. So let's have to have a look in each and every questions of NCERT, and if you have any doubt, please ask me. Try to solve the latest PYQs. You will get cover each and every topic. Okay, you will do each and every topic. I have covered according to this. Okay, so get ready for the BTS part 2, and have a nice day. Thank you.